Okay, so today we're going to talk about the dimension of the matrix. So, the dimension of the matrix. In the last tutorial, as I said, we discussed about the basis and the linear independency, and then we have defined what is the basis of the vector. So, in connection to that, we will talk about the dimension of the vector space. So, what do we mean by the dimension of the vector space? I'll explain you in very simple terms. So, when we go for a reduction of a matrix, say we have a matrix A, and we go the matrix A reduction to row reduction to R matrix. So then if we have the number of non-zero rows, so that defines the dimension of the vector space. So to understand it better, so let us go with the definitions, and then we will see these relations. So here the one definition is that, I'll come to the actual definition later. We'll consider if there is a vector v1 and up to vector vm, and if we have the another vector, say w1 to say wn, and or both bases for the same vector space, then it is m should be equal to n. So now to understand this, let us consider the case where we have the more number of columns than the rows, and if we then each w is a combination of vector v, so that can be written as, if the capital W is equal to, so if we have the w1 w2 which is in the form of columns, so wn, so which should be equal to, here we have v1 to dash vm, which is multiplied by a vector. So if it is multiplied by a vector, say if it is multiplied by a matrix, that is a11 to a1n, the number of columns, so likewise we have am1 to amn, then this will result in, that is v into a. So this results in v into a, and the second vector, that is v2, is also, so here the vector w1 and w2 is a combination of v's, and here that is ax is equal to 0 gives us, so if ax is equal to 0, then it will give us, that is v into ax is also equal to 0, in which case we will get our wx, the unknowns, is also equal to 0. So a linear combination of w's gives us the 0. So let us now come to the dimension here. So the definition of the dimension, so it goes like this. Here the dimension of a space is the number of vectors in every basis. So that is what I said before in the beginning of this tutorial, that the dimension is the number of non-zero rows in the reduced row matrix. So that defines the dimension of the matrix. So the same thing which is stated here, the dimension of the space is the number of vectors in every basis. So now we'll talk about the basis for the matrix space and the function space. We'll just take quick points here. We'll not go in much detail here. So we'll see for the different dimension of the matrix, what is the dimension that it holds. Now for example, the dimension of whole n by n matrix space is n square, is actually n square. So if we have the n cross n matrix, then its dimension is the whole space is n square. So second point is that the dimension of subspace of upper triangular matrices is, so if you have the subspace of upper triangular matrix, then what is its dimension? Then its dimension is defined as, so half n square plus half n. So its dimension is defined as half n square plus half n. So that is what it defines here. So then for the next case, the dimension of subspace of diagonal matrix is n. So the dimension of the diagonal matrix results in n, and if we write the next point here, the dimension of subspace of symmetric matrices is, so that is given by half n square, that is given by half n square plus half n. So if you look into this second point and this last point, the dimension of the matrix is seen, that is half n square plus half n. So these are the few points which we have to remember when we are dealing with the dimension of the matrix. So if it is n cross n matrix, then its dimension is n square. If the dimension of the upper triangular matrix results in half n square plus half n, and the dimension of a diagonal matrix results in n, that is the number of columns. So n defines the number of columns here, and the dimension of the subspace of symmetric matrix results in half n square plus half n. So that is about the dimension of the matrix. So next we'll talk about the dimension of the four subspaces. So let me save this page here. Page 1. Let me take the new page here. So now we will talk about the dimension of four subspaces. So here we are trying to relate the rank of the matrix and the dimension of the matrix. So what is the rank of the matrix exactly? So the rank of the matrix is nothing but it defines the number of pivots in the column. So when we look into the column in a reduced form, so how many pivots we have, how many columns we get the pivots, so that defines the rank of the matrix. The dimension is nothing but the dimension of the subspace is the number of vectors in a basis. So now the rank of A reveals the dimension of all four fundamental subspaces. So let us write the four fundamental subspaces here, which are the spaces that we are talking about. The four fundamental subspaces. So in that first one, the row space. See, do not get confused with the spaces here. We are talking about the row space and the column space. So what is a row space? So the row space is nothing but if we transpose the matrix and bring it in the column form, so that we define it as the column of A transpose. We have done this in the previous tutorials. You can just refer it. So the row space is C of A transpose a subspace of R power n. So if you're talking about the row space, then it depends on the dimension of the number of columns. So for example, if we have here say m cross n matrix, so let us consider that it is a 3 cross 5 matrix. Then if we talk about the row space, then the row space can be defined in terms of the column of A transpose. I don't have much space, I'll write it below. So it is defined as the column of A transpose. We will take the transpose of A, so that defines the column of the rows, and the subspace, now it is a subspace of dimension r power 5 for this example. In general, we can write this as r power n. So we can write this as in general r power n because the row space depends on the dimension of n. Now let us write the second point here. So the second point, it states, now we'll talk about the column space. The column space is C of A. It is just the matrix A, and we just take the column, and a subspace, and it is a subspace of rows, row dimension. Now subspace of, now we'll define in general. Now for this above example, it is actually r power 3. It means it related to a three-dimensional case. So if we talk the column space, then that column space exists, or it is a subspace of a, the column space is a subspace of a three-dimensional three-dimension case. Whereas if I write this in a general form, then it will be r power m. Now let's talk about the null spaces. So the third point is the null space is n of a subspace. It is a subspace of, it is in general, it is related to the number of columns. The dimension is restricted to the number of columns. So it is n of a is a subspace of r power n. These are very important, which we have to remember it. So there is a one more subspace which we are talking about. The one more subspace is the left side of the null space. So if we take the transpose of the null space and it moves to the left side, so that we are talking about. So the left null space, the left null space is, I'll write that later, is a subspace of, now when we take the transpose of this null space n of a, so now it is in terms of rows. Now it is not in terms of columns. So in terms of rows, then it is represented as n of a transpose. So then it is subspace of, that is r power m. So these are the four fundamental subspaces which we should know about it. Now we'll take one example here to understand. Okay, before going to that, there is one point. So null space of A and null space of A transpose have dimensions. So we'll relate this to its, we'll talk about its dimension quickly. So the n of A, the null space of A has the dimension, its dimension, so let me write this as D. Its dimension is given by n minus r. It means the number of columns minus rank of the matrix will define the dimension of this null matrix, this null space in terms of columns. So if we talk about the null space in terms of rows, that is n of A transpose, then its dimension, that is D, its dimension is defined as, it is m minus r, means it is the number of rows minus the rank of the column. So that defines the dimension of that. That is the left null space. Okay, so now let us take an example and understand here, like what is a four-dimensional subspace that we are talking about, the four dimensions. The four subspaces which we had defined here. So we have the four subspaces here, that is r power n, r power m, r power n, r power m, that are related to different spaces, that is row space, column space, null space, and left null space. These are all the subspaces of r power n. So row space is a subspace of r power n, column space is a subspace of r power m, and null space is a subspace of again r power m, and left null space is a subspace of r power m. So now let's take one example here. So I'll take one matrix, that is, so this is the reduced matrix. So 1 3 5 0 7. this is not the matrix A, this is the reduced matrix. Let me repeat that. It is a reduced matrix. So after reducing this matrix to echelon form, so we get the third row, that is the third row is equal to 0. So if you look into this case, so how many pivots we have here? So we have the pivot 1 here and we have the pivot 1 here. It means the rank of the matrix is equal to 2, and the number of pivots in columns, and which are the pivot columns. So if I talk about the pivot columns, so I'll just write COL to represent the columns. So the pivot columns are 1 and 4, and the pivot rows, if I talk in terms of a pivot row, then which are the pivot rows? The pivot row is 1 and 2. So 1 and 2 are the pivot rows. So this is actually a 3 cross, it's actually a 3 cross a 5 matrix. So the value of m is equal to 3 and n is equal to 5. So the rank of the matrix is equal to 2. Now the row space, the first point, now if you relate this with all these 4 fundamental subspaces, then this example, then the first one here is the row space of R has, what is the dimension of this? So the definition of the dimension we have written. I told you there are the number of non-zero rows defines the dimension of the matrix. So let us relate this, the row space R, and what is its dimension. So the first point, if I write here that the row space of R, what is the meaning of R? So this is R matrix, that is the reduced matrix, has the dimension. Now what is its dimension? So how many non-zero rows we have? So this is equal to 2. So the dimension is 2 and matching, and it is the dimension of the matrix is 2, and which is equal to the R of the matrix, that is the rank of the matrix. So let me write this is a reduced row matrix here, and the dimension of the row space is the rank. So in this case what happens, the dimension of the row space is the rank of the matrix. The non-zero rows of R forms the basis. Now what is the basis in this example? Which are the basis vectors? So the basis vector is, so let me write here, so the dimension D is 2, and which is equal to, that is the rank of the matrix, which is equal to 2, and the non-zero rows of R forms the basis. Now which are the non-zero rows which forms the basis? We talked about the basis vector in the previous tutorial. So in this case the basis row forms, that is in terms of row vector if I talk, so then it is 1 3 5 0 7 is one of the basis vector, and 0 0 0 1 2 is the another basis row vector. Okay, so this is one point. So then I'll erase this and we'll talk about the second subspace. Then if you talk about the second subspace here, the second point, then the in terms of the column space of R also has dimension R equal to 2. Now how many, if you, in terms of, if you talk about the column space, now there are 5 columns, out of which we have the 2 columns with pivots, and the dimension of the matrix is again, which is equal to D is equal to R, which is equal to 2 itself. And here we get the 2 special solutions when we talk about the column vectors. So there are 3 free variables. So this is a free column, this is a free column here, and this is a free column here, and we know how to get the special solution. So we'll get 3 special solutions here, and the pivot columns forms the basis in this case. So in the previous case the non-zero rows forms the basis for the row space. For the column space, what is the basis is, so let me write the definition here. So the dimension of column space is the rank R, so that we already know it. But what is the basis vector for this? The pivot columns, form a basis. The pivot column forms the basis. Now, which are the basis vector in this case? So if I write the basis vector here, so then my basis vector, that is B, so that is in terms of column vector, that is 1 0 0. So whenever we write with comma, it means it is the column vector. If I write these values without comma, it means it is the row vector. And the second basis vector is 0 1 0. We are not talking about whether this basis vector or dependent or independent, so that discussion will keep it aside. So we're just finding what are the basis vectors for the column space and for the row space. For the, let me repeat, for the row space, the non-zero rows forms the basis vector, and for the column space, the pivot column forms the basis vector. So now let's talk about the third point here with this example. So for that, let me remove this and let me write the third point. So now we'll talk about the null space, the fourth subspace which is there. So the null space dimension. So the null space dimension, as we have written here, so it depends on R power m, the dimension. Then here it relates to the null space. The null space has the dimension, which is given as, that is n minus r. Whereas for the row space, the dimension depends on the rank of the matrix, that is R, and for the column space, the dimension of the matrix depends again on R. But whereas for the null space, the dimension of the matrix is given by n minus R. For this above example, so here, so if we talk about what is the dimension of the null space, so we have the 5 columns here, so 5 minus the rank of the matrix is 2, so that is equal to 3. So it means the dimension of the matrix is equal to 3. It means it is, we can also relate this to have the number of free variables here. So we have the 3 free variables or the 3 free columns. So if I talk about in terms of variable, this is x1, the second column is x2, third column is x3, x4 and x5. Then x2, let me write it properly, that is x2, x3 and x5 are the free variables which doesn't have any pivots, and that forms the special solution. So that forms the special solutions. So we get the special solution here, that is S2. I'll leave it to you to find out the special solutions. I'll quickly write it here. So the special solutions we'll get as minus 3 1 0 0 0. In the previous tutorials we talked about how to find the special solutions. Okay, it's okay, I'll just give you the introduction to that special solution. So we have the 3 free variables, so make one free variable as 1 and other variable as 0, and try to equate that to the right side, bring it to the right side, and the pivots should match to it, and the scalar values of the pivots, so that gives the special solution. So S3 we will get this as minus 5 zeros, minus 5 0 1 0 0. Then we get S5 which is equal to, that is we'll get minus 7 0 0 minus 2 and 1. So these are the special solutions that we'll get, and this yields to, we know that the null space, if I talk about the reduced matrix form, then this is Rx should be equal to 0. So hope you understood the null space dimension. So let me revise. The null space dimension depends on the D is equal to n minus R. And what are the basis for this? So the basis for the row space was the number of non-zero rows, whereas for the columns, for the second point which we had discussed, this is the third point, for the second point the basis were actually the pivot columns or the basis, whereas for the null space, what are the basis? These special solutions, these 3 special solutions forms the basis vector for the null space. Okay, so let us go for the last subspace. let me erase this here. So let me talk about the last point here, that is the fourth subspace. So the null space in this case again it's also a null space, but it is a left null space where we have taken the transpose. If we take the transpose of this reduced matrix, this we call it as the left null space. This is left null space. Okay, and its dimension depends, the dimension d is equal to, it is m minus r. So it has the 3 rows, so this is given by, it is r minus 2, it is equal to 1. So we have the dimension of the matrix is equal to 1. So that's the dimension of the matrix for this left case. um, So the basis vector, it's not discussed here. So the basis vector, so for this case it is given as 0 0 1. So that can be written as, for example, we have the matrix here. So if, this can be written in terms of R transpose into Y is equal to 0, then the left space can be written as in terms of, say, y1 into the first row, that is 1 comma 3 comma 5, because now it is in terms of transpose. Let me write in this form itself so that you can understand. So now it is y1 into, we take the another variable, we don't take the x, so x is for the normal form, and the inverse we'll take this as y, unknowns. So this is 13507 plus, then y2 we have here, that is 0 0 0 1 2, and the third one is actually zeros, therefore y3 is actually 0. This is 0 0 0 0 0. So this results in all zeros. So to get this results in zeros, so the null space of R transpose contains the vector, that is y. So to make the right hand side which is equal to 0 here, so if I want to make this as 0, then definitely this y1 has to be 0, this y2 has to be 0, because these scalar values or these unknown values should be 0, then only it will become the null space. It should be equal to the null space vector, that is the right hand side of the 0. Whereas the y3 need not to be 0, because anyway its vector is 0, it can be any value, doesn't matter, because its vector is 0. So therefore the vector of y can be, the solution for this case is actually 0 0 and y3. The solution, the special solution for this case is 0 0 y3, and so for example we can take y3 as 1, then the basis of this vector is given as 0 comma 0 comma 1. So this forms the basis for the null space for the left R transpose. So this completes our discussion with respect to the 4 subspaces which we have started with, uh, the 4 fundamental subspaces. Now we have defined what is its dimension, what is the dimension for the row space, and what is the basis vector for row space. So if you want to just quickly revise, then the row space has the subspace, a subspace of R power n. It has a dimension which is R is equal, its dimension d is given by the non-zero rows, and the basis vector is the non-zero rows, defines the basis of the vector, whereas in the column its subspace, it's belong to the subspace of R power m, and its dimension depends on the, again, the rank of the matrix, that is R, and the basis forms the pivot columns, forms the basis for this column space. Whereas when we talk about the third point, the null space, so the dimension of the matrix is defined by n minus R. So n is the number of columns, minus R is the rank of the matrix, so that defines the dimension of the matrix. And the subspace, the basis is nothing but the special solution forms the basis for this third null space. So when we talk about the left null space, then the dimension of the matrix is defined as D is equal to M minus R. So that is nothing but 1. The dimension of the matrix is 1, and its basis vector is defined by, say, if we have these 3 columns after the transpose, then it is 0, 0, 1 for this case. So that's it for this case. So let's take one example here to make you understand these dimension of the subspace and other things. So let me save this page here. Oh no, that's something else which I saved it. Okay, anyway. So let's take one quick example here. So I'll define the question first, so then we will go for the solution of it. So the question is here, test whether the following vectors, that is 1, 1, minus 1, 0, then we have 4, 4, minus 3, 1, and we have one more vector here that is minus 6, 2, 2, 2, and we have one more vector here that is 9, 9, minus 6, 3. Test whether these vectors are linear dependent or linear independent. Also find the dimension, and basis. Since we have taken only the matrix A, and remember that when the vectors are written in this form, so here there are no comma in between the values, so it means it's a row vector. So please do not write this in a column vector. So if I write this in terms of matrix A, so here it is not defined whether it is the null space matrix or anything, so it's just given this matrix A. So it is 1, 1, minus 1, 0, then it is 4, 4. I think I have written some extra values here. So it's actually 4, 4, minus 3. So this 4 is not there. Okay. So it's 4, 4, minus 3, 1. So it is minus 6, 2, 2, 2, and I have 9, 9, minus 6, 3. So now what we have to do is that we have to bring this to the reduced form. So let's start this with bringing to the reduced form. So what I'll do is that so row 2, I'll replace the row 2 with row 2 minus 4 times the row 1. So then what do I get? So first row will remain to be as it is, so it is 1, 1, minus 1, 0, and then the 4 times of this minus, so here I will get 0, 0, so here I will get this as so 4 times this is minus of minus, so here I will get minus 1, minus of plus, I'll get so minus of minus, so it is, I'll get here the plus 1, so here I'll get plus 1, and here I'll get 1 here. So then here the row 3, I'll replace the row 3 with row 3 minus of minus 6 R1. So then I'll get here this is 0, and I'll get here as 8 because it is plus, it is 6. I'll get here 8, and then here I'll get minus 4 and 2. So here you multiply with plus 6, you'll get 6 minus 2, 4, and here you'll get this as 2. And the last row, that is R4, you replace the R4 with R4 minus 9 times the R1, then I'll get here as 0, and here I'll get 0, then 0, here I'll get this as 3, so because it is 9, and here minus of minus plus, and so I'll get plus 3, and here I'll get the plus 3. So this is the one step of elimination. Now if you look here, we have the 0 and here 8. So what we can do is that we can interchange the rows. We can use the permutation matrix, if you remember that we are discussing very early tutorials. So we can use that permutation matrix and we can interchange the rows, and I can write here. So here I will write that is R2 is interchanged with R3. So then it is 1 1 minus 1 0, and here I'll get 0 8, then minus 4 2, and then I'll get here the 0 0 1 1, and this is 0 0 3 3. Alright, so I need this matrix to further reduce it, so I'll copy this matrix here and I'll paste it here. Okay, so this is our matrix here. So let us go with the further reduction. So further reduction is that, so this R4 is replaced by R4 minus 3 times the R3, new one. So then I'll get here this as 1 1 minus 1 0 0 8. So I'll get here 0 8 minus 4 2, and this is 0 0 1 1, and here I'll get this as 0 0 0 0. So the last row has become 0 here. So we will if you want we can continue. So so we got the pivot, so let us identify the pivots here. So the pivots we get here, this is 1, and we have the 8, and this is 1. So basically we can divide this row by the value of pivot to neutralize this. So then we can get, and whereas this is the last column is the free column we can talk about. So here the number of given vectors are 4. It means the dimension of the matrix, that is m cross n, is actually a 4 cross 4 matrix. So when it is a 4 cross 4 matrix, here the rank of the matrix, if I see, so what is the rank of the matrix here? The rank of the matrix is equal to the number of pivots. So here we have the 3 pivot columns, so the rank of the matrix is equal to 3 here, therefore the dimension of this matrix. So how do we see the dimension of the matrix? Either you can see this as the row space, or you can see as the column space. The dimension of the matrix is equal to 3. Right, now it depends. Now if you see this in terms of the row space, if we talk about the row space, just hold on. So yeah, if we see this reduced matrix as the row space, then what is my basis vector? So my basis vector is nothing but the non-zero rows. So the non-zero rows is, that is 1 1 minus 1 0, and this 0 8, sorry, 0 8, sorry, 0 8 minus 4 2, and the last row is 0 0 1 1. So this is my basis vector, and whether this is linearly dependent or independent. So that is another question that we have here. So is this a linearly independent, or this is linear dependent? What is the right one? So for linearly dependent, the number of rank of the matrix should be equal to the number of columns of the matrix for linear independency. Therefore it is not the linear independent case, it is linear dependent case. So because the combination of these pivot vectors will form the other columns to be generated, or it fills the span, so therefore it is linear dependent. Now if I talk about this in terms of the column space, what is its vector? So let me write this as BR. So in terms of the column space BC, if I talk about, then its special solutions will form. So how many special solutions I can have in this case? So for that I have to go for again further reduced row. I have not reduced this. I have to make these columns the upper values as 0 here. Then if I neutralize this, I don't have enough space to write here. So if you divide this, then I get this is divide by 8, I'll get here half, and here I'll get 2 by 4. So 2 by 4, then here I have to remove these values here, then I'll subtract this above values. So nevertheless, so if I write this in a complete reduced form, then I'll get here this is 1, and I don't know what exactly I'll get here. So before that, let me divide this by 8, so I'll get here this is 1 by 2, and this is 1 by 4 I'll get, and this is 0 0 1 1, and the last anyway it is 0 0 0 0 here, and so this is the value. So here I need to just add with -1. So what happens, so this will become 0 here, and this I'll get here as -1 minus half. So -1 minus half, what do I get here? So I'll get the -2 minus 1 by 2, so I'll get -3 by 2. So I'll get -3 by 2 here. So I'll get -3 by 2, and here I'll get this as 1 by 4. So here I'll get 1 by 4. So I reduce this. Now I have to bring this to 0 by multiplying this row with this, then with this. So anyway, I'll leave it to you to figure it out, and then the special solution which we'll get. So basically we'll get one special solution in this case because we have only one free column. So before that I have to make this as 0. So if okay, let me try to simplify this, then the one more row here I'll get this as 0 0. So here I have to multiply with it has become a little complicated. So 2 by 3, 2 by 3. So multiply this by 2 by 3, then 3 by 2 minus, no, to get this to 2 by 3 here is so what I need to do is that 2 by 3. So this will make it as 1, but it doesn't make it as 0. Okay, fine. Why do I need to make this? So -3 by 2, then it is a -3 by 2 I have to multiply, so this will become 0 here, so this will be 0. So then I'll multiply this as -3 by 2, then it is 1 by 4 minus 3 by 2. What do I get here? That is 4 by 8. Then 4 by 8 is oh, this is really getting a little complicated. So I'll not cover this in this tutorial, so I'll leave it to you to figure out these calculations. So the last value is I'll get here 1 minus 3. It's not exactly, it's 8, so it is 2 4, so it is something which we'll get here. So I'll leave it to you to figure out what is the final reduced row matrix, and I'll just tell you one thing, that is we will get here one special solution. So the basis of the vector for the column space, we will get just one particular special solution. So that is the basis vector for this. So hope you understood this example. We have covered this dimension of this matrix. So yeah, that's it for this session. So in the next session we'll talk about the orthogonality of these 4 subspaces. Thank you.